Hi class, in this third section of Chapter 6 we want to look at, again, some things about telescopes, but now we want to talk about where you would put them. So do you put them up on the ground, do you put them on mountains, do you put them in space, where do you put them and why would you put them there? So there are four things basically that you want to think about that are sort of good for telescopes. You don't want it to be windy, you don't want the atmosphere above you to be kind of thick and turbulent. All right, you don't want it to be bright, so you want to be away from city lights, and you don't want it to be moist. You don't want a lot of humidity. So all those things will affect the images and the clarity of the things that you're trying to see. So you don't want it to be windy, so you want to be somewhere where it's fairly calm. You want to be up as high as you can so there's less atmosphere between you and the stars. Being up high in a mountain doesn't mean that you're necessarily closer to the stars. It doesn't help in that respect, but it helps diminish the sort of the jitteriness of the image because of the atmosphere. So the less atmosphere you have to look through, the better. And you want it to be dark, of course, because the light, especially when you're looking at stars in the visible part of the spectrum, visible light from cities and stuff will interfere with your images. And you don't want it to be moist again, because moisture is also going to affect your images. It's going to cause them to be blurry, or you might even have clouds, of course. It's hard to see through clouds depending on what you're trying to look at. So light pollution is a big issue, and this is a little image of the United States and South America. But look at all the lights up in North America here. Look at how bright Chicago is right there, the Chicago area. So there's a lot of light pollution in our area, and so having big telescopes around here, we can see things, but it's not the best place to be. We'd probably want to have a telescope if we were to spend a lot of money and try to do a lot of research in astronomy. We certainly wouldn't want to build a telescope anywhere near Chicago. We'd want to be way out here maybe in the desert where it's really dark, maybe up on a mountain, or somewhere out in the ocean, perhaps up on a mountain, and to get away from all this light. There are a lot of cities actually now that are doing light pollution mitigation, and they're changing the lights that they use so that less light reflects back up into space and it all just kind of shines down where it's needed. So a lot of cities have done a good job of just changing their lights to do that, to avoid all the wasted light. Another thing that we can do with telescopes on the ground, there's going to be some atmosphere that they have to look through. Even if they're really high up on a mountain, there will be some atmosphere that they're having to look through. And that atmosphere is going to make the images look a little blurry, because as the light comes through the atmosphere, the air is always moving around to some degree, and that's going to make the images a little bit blurry. If you ever look like on a hot road, if you're driving down the road and you look across the road and it's warm, you often see kind of a fuzziness of the images look kind of fuzzy because of the heat rising up off the road. Or if you have a grill out in your backyard and you're cooking some food, and especially if there's some moisture in the air, just above the grill you can kind of see this waviness of the air. You see that turbulence because of the heat rising off the grill. So that's that kind of turbulence that you're trying to avoid in astronomy. And there's always something. Even if it's really calm and cool, there's always some turbulence. The calmer it is, the cooler it is, the better it is. But there's always something. So what astronomers have done is they use something, there's a couple things, but one thing they do is they use something called adaptive optics, where they actually take the mirror of the telescope and they make it flexible. And so they have a computer connected to the mirror with all these little tiny fingers underneath the mirror that make the mirror change its shape to compensate for the changing atmosphere. And so they use a laser they shine up into the sky, and the telescope can see the image of the laser reflected back. And the computer, in real time, looks at how the image of the laser is fluctuating, and it compensates for that, and it changes by changing the shape of the mirror many times a second. And so it's really a high-tech technique of compensating for the motion of the atmosphere, the turbulence in the atmosphere. So this can only be done with reflecting telescopes, because the mirror can be made to be thin and flexible. You don't have to have a piece of glass that the light goes through to be focused. That piece of glass in the refracting telescopes is thick and heavy. You can't bend to that. You can't do anything to that. But the reflecting telescopes have mirrors, and those mirrors can be made to be fairly thin. They can also be segmented, and so you can adjust the mirrors fairly easy with telescopes or with computers. So here's an example of an image without adaptive optics, and it looks like one star. And again, this is a zoomed in image, but you can kind of see the rings around it like we talked about before, but it looks like there's just one object here. If you use adaptive optics, that one object actually becomes two. So this is the same size image, but you can clearly see there's two things there. And again, you can see these little rings around it, and that's that diffraction we've been talking about. But you've increased the angular resolution of the telescope by not making the telescope bigger, but just by making it better, by allowing it to compensate for the atmosphere, by being able to change the mirror's shape in such a way to compensate for the atmosphere of the turbulence in the atmosphere. So you can also put telescopes up on mountains, and that's what you usually try to do. So this is the example. We talked about this a little bit before. Mauna Kea, the volcano in Hawaii. These are the two Keck telescopes that we had looked at before, and there's other telescopes up on the mountain too. So up on top of this mountain, you're not up on a mountain because you want to be closer to the stars. The difference, your distance is negligible from the ocean to the top of the mountain in terms of the distance to the stars, so it makes really no difference. But it's that you want to get above a lot of the weather, for one thing. You're above a lot of the clouds, and you're looking through less atmosphere. It's usually calmer, it's usually drier, there's less atmosphere to affect your images, and less oxygen. So if you're going to live up here, maybe you might have to actually use an oxygen mask or something occasionally, or just get used to it somehow. So we put the best observatories up on the tallest mountains in the driest climates. And then we could put telescopes in space, and that's a bit more expensive, but it gives you the best images, because in space, of course, there is no atmosphere. So you can get very, very clear images. You don't have to use adaptive optics to compensate for any atmospheric blurring. But it's expensive, it's hard to do. But this is the Hubble Space Telescope, so this has been up there for quite a while now, and it's still being used, but it's nearing the end of its life. And in place of it, they're building the James Webb Telescope. This will be going up sometime in the near future. It'll be launched, and it'll take the place of the Hubble. It's a very different looking telescope. It's bigger than the Hubble, it has better technology in it, but it's going to ultimately have really, really nice images of a lot of stuff. So why would you put telescopes in space other than the atmosphere, seeing through the atmosphere? Well, there are many actually, wavelengths of light that actually don't make it through the atmosphere, and that's a good thing. Most of the gamma rays, so there are objects in space that give off gamma rays, and gamma rays can penetrate into the atmosphere. So these arrows coming down are kind of an indication of how far into the atmosphere certain things can go. Luckily for us, our atmosphere blocks gamma rays. So that's a good thing, because they're very damaging. They could hurt us. So our atmosphere blocks them. So if you want to see the gamma rays that something is emitting, you need to put a telescope out in space. And so there's something called the Fermi telescope or the Swift Observatory. Those are telescopes in space that detect gamma rays from objects. So they have to be in space. X-rays also are blocked by our atmosphere. So you have to put, again, a telescope up in space to see the X-rays that objects emit. And the Chandra X-ray Observatory is one such telescope. The Hubble Space Telescope sees in the infrared as well as the visible, and a little bit in the ultraviolet, so in that visible range, near the visible range. And so that's up in space, not necessarily because it has to be, but because it's just better that way. And it just can see much, much better. With adaptive optics, some telescopes on the ground can see just as good as the Hubble Space Telescope. And so the James Webb Telescope is going to be eventually much bigger. That's this. And it's going to see even better than any ground-based telescope when it's launched. And then in the infrared, so visible can make it to the ground. So you don't necessarily have to put a visible light telescope up in space, but it does usually work out better. But then these other wavelengths, infrared, for example, if you wanted to look at objects that are giving off infrared light, that light does penetrate the atmosphere. It goes pretty far down. So there are some observatories, there are some telescopes. There's one called Sophia, I believe is the name. It's actually in an airplane. So they fly a 747, I think, around, and the telescope is actually in the airplane. And they fly really high where the atmosphere is steady, so the airplane is flying in a fairly smooth layer of atmosphere. And they open up, kind of a side, there's a sort of a clear side window that is opened up, and the telescope can look out in space from the flying airplane. And so they use that, or they can put a telescope literally out in orbit around the Earth, and it can look at the infrared light given off by objects too. One thing about infrared light is, because hot objects give off infrared light, like you and me, we're infrared light bulbs. you don't want an infrared telescope near anything that's warm, because those warm things are gonna interfere with what it's trying to see. And so that infrared telescope itself also has to be cooled to very low temperature, so its own heat doesn't interfere with what it's trying to see. So space is a good place for an infrared telescope because it's nice and cool up there. And then there's also something called the Planck Observatory that detects like microwave radiation from things. And then radio waves do penetrate down very easily, quite well. And so radio telescopes that look like big satellite dishes, those can be placed on the ground, and many of them are placed on the ground. And that's actually just fine. There's not a huge need to put a radio telescope up in space. It would still help, but that's actually pretty difficult because, as we'll talk about later, the size of a telescope, as the wavelength gets bigger, so radio waves have a big long wavelength, gamma rays have a short wavelength, and everything else is in between. As the wavelength gets bigger, in order to get good angular resolution, the telescope has to be even bigger. So we talked about how the size of a telescope affects the angular resolution and the light gathering power. But there's also, in terms of angular resolution, there's also an effect of the wavelength. And so the bigger the wavelength, the even bigger the telescope must be to get the same sort of angular resolution. So these radio telescopes can be very large. And so it's, right now at least, it's pretty impractical to put them in space. Someday we might put one on the moon maybe and have it sort of stationed on the moon. So there's very little atmosphere on the moon. That might be a good thing to do at some point, but that's going to be expensive. So there may not be a huge advantage to doing that just yet. So those are the reasons why you might want to put telescopes up in space, primarily because many of those wavelengths you're trying to see simply don't make it to the ground, and so you can't see them from the ground. There's a little interactive figure that we can play with, and it's available in our site, in our D2L site. This neat little thing. What you do with this is you take your observatory and you can move it up around. You can move it up in altitude. And so right now it says we're looking at X-rays. We're asking about X-rays, and it says no X-ray radiation penetrates to this depth, so to the ground. If you move your telescope up a little bit, now you can be in an airplane. It still says no X-rays penetrate to this depth. If we come up a little bit higher, a little bit higher, a little bit higher, no, still no X-rays penetrate to this depth. We keep going higher and higher. Now we're kind of in a rocket or something. Still no X-rays penetrate to this depth. Let's keep going up, 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 up. And now we can get to a height where we can see the X-rays. And so this is an image of the sun giving off X-rays. There are certain things that are happening on the surface of the sun where X-rays are being emitted, big solar storms. All right, and so those are bad. We don't want to get hit by those X-rays. So luckily, our atmosphere protects us. But if we want to take pictures of the sun and see what's going on the sun, and to really understand what's going on, we need to take pictures of all the different wavelengths of light coming from the sun. To take X-ray pictures, we have to actually put our spacecraft, our telescope, up into space. And so we do have orbiting spacecraft that are constantly monitoring the sun, looking at the X-rays the sun gives off, and visible light and other wavelengths as well. So you can play with this, and you can check other wavelengths, like if I want to go to, say, infrared, for example. Here's an image of the sun in infrared light. Infrared penetrates pretty far down. Might not penetrate all the way down, but it penetrates pretty far down. But as always, the higher you are, the better. You're just going to always get a better image. You're going to see more clearly because of the lack of atmosphere. And so this is, again, an image of the sun in infrared. So if we brought our observatory all the way to the ground, eventually the atmosphere blocks out all that infrared light, and so we can't see much down here. Plus, you're going to be near a lot of warm things like the ground itself, and the telescope, the infrared telescope down here, just might not work very well. Radio waves, we can be pretty much anywhere to see radio waves. They penetrate all the way to the ground. So this is an image of the sun taken in terms of the radio waves that it gives off. So looking at all these different colors, all these different wavelengths that objects give off, can tell us a lot about the objects and what the different processes going on in those objects. So we'll be talking about a lot of those things in the near future here. So in this section, we just basically talked about the atmosphere and why we would put telescopes in different places. And so again, you want the telescopes to be basically in a place where there's not a lot of wind, where there's no moisture, where there's little warmth, little heat. You want it to be cool and dry, and ideally, the best place would be out in space. but in some cases it's not that practical to do just yet. So that's all for section 3.